The training process for a neural network is a fascinating blend of math, computer science, and a bit of art. It's how these networks learn to perform tasks like image recognition, natural language processing, and more. Here's a breakdown of the key steps. 1. Data collection and preparation. Gather data. The first step is to collect a relevant data set for the task you want the network to perform. For example, if you're training a network to recognize cats versus dogs, you'd need a large data set of images labeled as either cat or dog. Data pre-processing. Raw data often needs cleaning and preparation. This might involve resizing images, making all images the same size, normalizing data, scaling pixel values to a standard range, e.g., 0 to 1. Data augmentation. Creating slightly modified versions of existing data, e.g., rotating images, adding noise, to increase the size and diversity of the training set, which helps prevent overfitting. Splitting data. The dataset is typically split into 3 parts. Training set, the largest portion, used to train the network. Validation set, used to evaluate the network's performance during training and tune hyperparameters. Test set, used to evaluate the final performance of the trained network on unseen data. 2. Network architecture. Define the architecture. You need to choose the type of neural network, e.g., convolutional neural network for images, recurrent neural network for sequences, and its architecture, number of layers, number of neurons per layer, types of connections. This is often based on experience, research, or experimentation. Initialize weights. The connections between neurons have associated weights. These weights are initialized randomly at the beginning of training. These initial random values will be adjusted during the training process. 3. Forward pass. Input data. A batch of data from the training set is fed into the network. Calculations. The input data propagates through the network, layer by layer. Each neuron performs a calculation based on its inputs, weights, and an activation function. The activation function introduces nonlinearity, which is crucial for the network to learn complex patterns. Output. The network produces an output, e.g., a classification label, a predicted value. 4. Loss. Function. Calculate error. The network's output is compared to the actual target value, the correct answer. A loss function quantifies the difference between the prediction and the target. The goal of training is to minimize this loss. Different loss functions are used depending on the task. 5. Backpropagation. Calculate gradients. The algorithm calculates the gradients of the loss function with respect to each weight in the network. The gradient indicates the direction and magnitude of the steepest ascent of the loss function. Propagate gradients. These gradients are propagated back through the network, from the output layer to the input layer. 6. Optimization. Update weights. The weights of the network are adjusted based on the calculated gradients. An optimizer algorithm is used to determine how much to adjust each weight. The goal is to move the weights in a direction that minimizes the loss function. Learning rate. A crucial parameter called the learning rate controls the size of the weight updates. A small learning rate might lead to slow convergence, while a large learning rate might cause the network to overshoot. 7. Iteration. Repeat steps. 3 to 6. The process of forward pass, loss calculation, backpropagation, and weight update is repeated many times, iterating over the training data, multiple epochs. An epoch is one complete pass through the entire training dataset. 8. Validation and tuning. Evaluate on validation set. After each epoch, the network's performance is evaluated on the validation set. This helps to monitor the training progress and detect overfitting. Tune hyperparameters. Based on the validation performance, you might need to adjust hyperparameters. 9. Testing. Evaluate on test set. Once the training is complete and the hyperparameters are tuned, the final performance of the network is evaluated on the held-out test set. This provides an unbiased estimate of how well the network will perform on new, unseen data.